Welcome to this explainer. Today, we're diving into the absolute spectacle of atmospheric science behind one of nature's most terrifying and honestly awe-inspiring displays. We're going to look at exactly how a simple, seemingly harmless cloud transforms into a dynamic electrical engine, an engine capable of splitting massive trees, sparking wildfires, and literally disrupting our modern infrastructure. Okay, let's kick things off with a totally staggering fact. A single bolt of lightning? It heats the surrounding air to 30,000 degrees Celsius. Just to put that into perspective for you, that is roughly 5 times hotter than the surface of the sun. No way, right? And yet, this violent, massive release of atmospheric energy happens in just a tiny fraction of a second. But here's the crazy part. This isn't some rare anomaly. We're talking about more than 8 million of these strikes hitting the Earth every single day. If you break that down, that is nearly 100 lightning flashes happening somewhere on our planet every single second. It's just a constant, massive transfer of energy.
Section 1. Anatomy of a thunderstorm.
So, to understand how a cloud generates all this electricity, we first need to dive into the troposphere and look at these towering cumulonimbus clouds. Think of them as giant natural electrical generators. We are talking about massive structures extending 12 to 18 kilometers up into the sky. Inside this huge vertical space, violent updrafts cause ice crystals, water droplets, and hail to just constantly crash into one another. It's kind of like static electricity building up when you rub a balloon against your hair, but on a massive, terrifying scale.
Now let's see how this engine actually powers up. It all starts with a simple patch of warm, moist, rising air that cools and condenses. And because this rising air stays warmer than the air around it, it acts exactly like a hot air balloon, accelerating into these powerful updrafts. All those constant ice and water collisions we just talked about, they physically separate the electrical charges inside the cloud, totally priming it for a massive discharge. Meteorologists actually track this storm life cycle through 3 distinct phases. It begins with the cumulus stage, right as the cloud grows. Then it hits the really violent mature stage. That's when it unleashes heavy rain, hail, and, of course, lightning. Finally, the dissipating stage takes over. This is where cool downdrafts essentially choke off the storm's supply of warm air. It basically starves the engine until the whole thing shuts down. And, as you probably know, you absolutely can't have thunder without lightning. The lightning is the actual electrical discharge branching out, desperately seeking the path of least atmospheric resistance. That instant blinding flash heats the air so rapidly that it actually expands explosively. So, that resulting supersonic shockwave rolling through the atmosphere, that is the exact boom we hear as thunder.
Section 2. Escalating threats. Categorizing the danger.
Because as you might expect, not all thunderstorms are created equal, right? Understanding their different types really helps us accurately gauge the threat level to our communities. From a quick summer downpour in a single-cell storm to the sheer devastating power of a supercell, the threats scale up rapidly. A supercell is particularly terrifying because it acts as a rotating, self-sustaining engine. It features this rotating updraft called a mesocyclone, which, by the way, is the exact mechanism that produces giant hail and devastating tornadoes.
And just as storms vary, well, so does the lightning itself. Intra-cloud lightning is by far the most common, but cloud-to-ground is the most dangerous to us down here. However, you've got to pay special attention to positive lightning. Originating from the very top of the storm, this highly charged bolt can strike the ground literally miles or kilometers away. It often strikes under a totally blue sky where it isn't even raining yet. Talk about a nasty surprise.
Section 3. The human and economic impact. Because beyond the awe-inspiring science, these atmospheric engines have a profound and sometimes catastrophic impact on human life, our supply chains, and the global economy. Real-world case studies constantly remind us that geography strongly dictates risk, and honestly, a lack of lightning awareness can be incredibly deadly. Whether it's exposed hikers caught on a jagged mountain ridge in Colorado or a sudden supercell in Australia causing hundreds of millions in hail and wind damage, the hazards are multifaceted and severe absolutely everywhere. In India particularly, the combination of intense summer heat, the shifting monsoon circulation, and a really vast rural workforce makes it one of the highest risk environments on Earth. States like Odisha and Bihar sadly see thousands of fatalities annually, and this highlights exactly why localized early warning systems are absolutely crucial for survival.
Which naturally brings us to a critical question. With all our modern science and massive satellite arrays, can we actually predict when and where a storm will strike?
Section 4. Engineering against the storm. Well, the short answer is yes, we can forecast broader conditions hours or even days in advance, even if we can't pinpoint a single individual lightning strike. To pull this off, scientists combine an incredible array of high-tech tools. They use Doppler radar to track the internal rotation of a storm, overlap that with geostationary satellite feeds, and then run all that data through AI-driven numerical weather models. This massive network allows meteorologists to issue life-saving warnings long before a squall line even arrives.
But we don't just predict, we physically protect our infrastructure. Did you know commercial airplanes get struck by lightning fairly regularly? It's true, but because engineers design the aircraft skin with continuous conductive pathways, the current flows harmlessly right around the cabin. Back down on the ground, smart grids are brilliantly designed to automatically reroute power to minimize blackouts when a substation takes a direct hit.
Okay, let's take a second to clear up a dangerous, widespread misconception. Lots of people think that if you are in a car during a storm, the rubber tires insulate you from the ground. Actually, scratch that. It is a total myth. It's actually the metal frame of the car acting as a Faraday cage that channels the electricity around you and safely into the ground. Those rubber tires do absolutely nothing to stop 30,000 degrees of plasma.
So here is a highly practical takeaway for you. If you ever want to know exactly how close the danger is, just use the thunder distance rule. Light travels faster than sound, right? Just count the seconds between the visual flash and the audible boom. Then divide that number by 3. That simple math will give you the approximate distance of the strike in kilometers. Easy to remember, and it might just save your life.
Now, the sheer power of this phenomenon also leaves behind a totally wild physical footprint on the Earth. When lightning strikes a beach or sandy soil, the intense heat can instantly melt the sand, fusing it into these fragile, hollow glass tubes called fulgurites. It's essentially fossilized lightning. How cool is that?
As we look to the future of disaster management, we have to acknowledge that changing weather patterns are fundamentally altering thunderstorm behaviors globally. But the next generation of technology is stepping up to meet this threat. We're talking about utilizing advanced space-based sensors and AI digital twins of our cities to perfectly simulate and prepare for an incoming supercell before a single drop of rain even falls.
The atmosphere is a dynamic electrical engine, and understanding its rules is the absolute first step in mastering our response to it. But as global temperatures continue to rise and storms grow ever more ferocious, the ultimate question remains, is our technology adapting fast enough to survive the superstorms of tomorrow? Thank you for joining this explainer. Stay curious, stay safe, and keep learning.